Chemflix. Calculating the pH of a weak acid. We're asked to calculate the pH of 0.45 molar CH3COOH. We look up this acid on the table, and it's called ethanoic, or more commonly, acetic acid. And because it's lower than the top 6 acids on the left side, it's a weak acid. To make this kind of calculation using a weak acid, we must use an ice table. Here's an ice table. Remember, I stands for the initial concentrations, C, the change in concentrations as the system approaches equilibrium, and E stands for the equilibrium concentrations. We write the equilibrium equation for the weak acid CH3COOH ionizing in water. Since the acid is weak, we write a double equilibrium arrow. It forms the hydronium ion and the ethanoate or acetate ion. We don't enter anything for the water. The initial concentration of the acid is 0.45 molar, so we write that in the I, or initial concentration box, under the acid. Before the ionization takes place, the concentrations of hydronium and acetate ions are both 0. We let X equal the increase in the concentration of hydronium as the system approaches equilibrium. Since the acetate ion has the same coefficient as hydronium, it will also increase by X. The CH3COH is on the other side of the equation, so its concentration will go down by X as it's ionized. So the equilibrium concentration of acetic acid will be 0.45 minus X. And the equilibrium concentrations of hydronium and acetate will both be 0 plus X equals X. Now we need to solve for X. Here's where we write the equilibrium constant expression for the ionization. Because this is a weak acid, we call the equilibrium constant Ka. The hydronium and acetate ions are the products, so they are written in the numerator. The acetic acid is the reactant, so it's written in the denominator. Since water is a liquid, we don't include it in the Ka expression. Now we plug in the values for the equilibrium concentrations of these in terms of X. The hydronium and acetate concentrations are both X, so the numerator is X times X, or X squared. And the equilibrium concentration of acetic acid is 0.45 minus X, so that goes in the denominator. To avoid having to use a quadratic, we realize that acetic acid is quite weak, so we make the assumption that the amount ionized, X, is insignificant compared to 0.45. So 0.45 minus X is almost equal to 0.45. When you're doing a question like this, you must state the assumption in your work. So we can state that Ka is approximately equal to X squared over 0.45. To find the value of X, we start by rearranging the equation to solve for X squared. So X squared equals 0.45 times Ka. We look up the Ka for ethanoic or acetic acid on the acid table, and it's 1.8 times 10 to the negative fifth. We substitute that in for Ka. Now we take the square root of both sides. So X, which is equal to the equilibrium concentration of hydronium, is equal to the square root of 0.45 times 1.8 times 10 to the negative fifth, which works out to be 2.846 times 10 to the negative third. Since it is a concentration, we use the unit m for molar. This is not the final answer, so we don't round it off to the correct number of significant figures yet. The next step is to calculate the pH. We have the hydronium ion concentration is 2.846 times 10 to the negative third molar. pH is the negative log of the hydronium ion concentration, which in this case is a negative log of 2.846 times 10 to the negative third. It comes out to 2.545765104 on a calculator. The lowest number of significant figures we had in our data, including the Ka value, was 2. Remember that in a pH, the significant figures start after the decimal point, so this needs to be rounded to 2 decimal places, which equals 2.55. You're not always required to do this, But at this point, we can test the assumption we made, the 0.45 minus x is almost equal to 0.45, by calculating the percent ionization of the 0.45 molar acetic acid. The formula for percent ionization, or percent dissociation, as it's also called, is the concentration of hydronium, which is equal to the amount of acid that ionized, over the original concentration of the acid times 100%. The concentration of hydronium in our sample was 2.846 times 10 to the negative third molar, and the original or initial concentration of the acid was 0.45 molar. So we plug these in and make the calculation. Notice the unit molarity will cancel. It comes out to 0.63%. The assumption we used is said to be valid if the percent ionization is less than 5%. Since 0.63% is much less than 5%, the assumption that 0.45 minus x is almost equal to 0.45 is valid in this case. In Chemistry 12 and BC, you're not expected to solve quadratics, so probably in any question you get, you can make this assumption. But remember, you must state the assumption as part of your work. I hope you found this useful. I have a huge number of resources to help you with on my Chemistry 12 webpage. Just Google Chem 12 and click the one called Chemistry 12 Called Your Chemistry. Bye.